Alright, let's look at our last notes for the unit, our third type of collision. This one, you might say, well, this isn't really a collision, it's an explosion. It still counts as a collision for conservation of momentum purposes, where momentum's always conserved for a collision, and explosions do count as a collision. This whole first part, right, what is a system, define conservation of momentum, we already did that in our bounce notes, so we can just cross that off. If you don't have that for some reason, you absolutely need to watch that video first, watch your bounce collision, then watch our inelastic collision, and then come back here. We already talked about this. If you're not sure, go ahead and review your notes in part 1. So, we are going to be using really the same process. We know, okay, momentum is conserved, set the total momentum before the collision equal to the total momentum after. Okay, well, let's go through an example. This is what an explosion is. It isn't always literally an explosion. It is two objects that start together, come apart. So, person in the boat example. What is the total momentum of the person-boat system at rest before the jump? They're at rest. Any object at rest, momentum is mass times velocity. If your velocity is 0, you have no momentum. So our person-boat system, treating them as one object, they have 0 momentum. They're not moving. Using conservation of momentum, we know whatever momentum they have before, they have to have after. So before they jumped, they had 0 momentum. They must have 0 momentum after they jump. Well, how's this possible? Right? Clearly the person is now moving. They jump to the right. How is this momentum 0? Well, when the person jumps to the right, the boat is actually going to be pushed back to the left. That momentum will cancel. The person has positive momentum. The boat has negative momentum. They will end up canceling so that as a system in total, the system still has 0 momentum. Now, if the momentum is equal, so total momentum before is equal to total momentum after. We're really saying after the jump, the momentum of the boat must be the magnitude, the absolute value of the momentum of the boat must be the same as the absolute value of the momentum of the person. And here we're just talking about absolute values, right? We know really the person would have a momentum to the right, positive. The boat would have a momentum to the left, negative. But the values, the number is the same. Compare how they're moving faster. Well, they have the same momentum. Momentum is mass times velocity. But the boat has a big mass. The person is a smaller mass compared to the boat. That must mean to have the same size momentum, the person must be moving faster, the boat must be moving slower. Overall, let's do a little recap on our different types of collisions. Our general conservation of momentum equation. This is not one that we are giving you on the test, but it is one you can derive pretty easily. Conservation of momentum just tells you before and after a collision, momentum in a system is the same. So that gives you the momentum of the objects added up, m1v1 plus m2v2, assuming you have 2 objects. Well, equals m1v1 prime plus m2v2 prime. This is for a bounce collision, but it's the foundation of all conservation of momentum. When objects bounce off each other, you just use this equation and solve. Plug in your masses, plug in your velocities. Last time, we talked about a perfectly inelastic. So that is when they hit and stick. Hit and stick. When they hit and stick, we know that before the collision, nothing is really changing. Right? It's still just the momentum of one object plus the momentum of the second object. But after they collide, they are hitting and sticking, hence the name. So the masses really combine into one mass. They're not traveling with different velocities anymore. They're essentially one object traveling together. This is like if you're on a skateboard, you catch a medicine ball, you go rolling back. You are one object, essentially, traveling together at some final velocity. What about an explosion? And this is our new part. For an explosion, well, the objects come apart, right? Here, in the end, after the collision, you have two separate objects. But before the collision, they are essentially one. They're traveling together. So, do really the opposite what you did with the hit and stick. In hit and stick, you combined the masses after the collision. For an explosion, you're just going to combine the masses before the collision. They start as one object, traveling with one common velocity. They explode, they separate into two separate objects. The reason we did our bounce collisions first is because if you always start with this equation right here, you can just read through the problem and identify, okay, if they're bouncing off of each other, if the objects end up separate, if they start separate and they end separate, that's a bounce collision. If they start separate and end together, that's a hit and stick. And if they start together and they end separate, that is an explosion. You can always start with this formula and then just make the tweak depending on what type of collision it is. Are they hitting and sticking? Are they exploding? You know, okay, you can combine masses if they're traveling together. Let's see what this actually looks like. This is an explosion problem, so we know we're going to use our explosion equation. The boat has a mass of 60 kilograms. The person has a mass of 45 kilograms. The person jumps from the boat at a velocity of 5 meters per second to the left. Calculate the resulting speed of the boat. Okay, well, we can draw our picture. The person is on the boat. They are traveling together. Here will be our boat. Here is our person, our stick figure. And we know the boat is a mass of 60 kilograms. The person is a mass of 45 kilograms. They are not moving. Their velocity together is 0. Okay. After the collision, what does it look like? Well, the boat, it's still 60 kilograms. We want to figure out the resulting speed, but we know the person, they're in the air, flying high. Their mass is still 45 kilograms. They jump from the boat at a velocity of 5 meters a second to the left. Okay, I'm just now rereading to the left. So let's go ahead, let's move them over right here. And let's move this over as well. Okay. So here's our person. We'll just do a quick flip-flop. They jump off. They are moving to the left. Velocity of -5. Okay. We set up our equation. Again, I would really recommend always use your big conservation of momentum equation. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. It's less to memorize. Identify. This is an explosion. The objects start attached, moving together. With that, we can rearrange and say, treat them as one object. m1 plus m2 traveling at some initial velocity equals m1v1 prime plus m2v2 prime. Now we're just going to plug in. The masses combined, 60 plus 45 gives you 105. We know the initial velocity is 0. This is a special case, right? What if the objects aren't moving? Well, they have no momentum. We will have situations where the objects are together moving as one. So our velocity is not always 0 here. In this case it is, does not have to be. Mass of object 1, well, let's call object 1 the person. So 45, their velocity is -5, plus the mass of the boat. We don't know that velocity, that's what we're solving for. Now we just go ahead and solve. We can rearrange this, bring this up to some workspace, maybe just over here. 105 times 0 is 0. 45 times -5 is going to give us -225 plus 60 v2 prime. Let's move our 225 over. Add it to both sides. 225 equals 60 v2 prime. Alright, hopefully you can still hear me over the bell. 225 equals 60 v2 prime. Go ahead and divide 225 divided by 60. gives you a velocity of our second object, the boat, after the collision, 3.75 meters per second. I get a positive value here, so of course that means the boat is moving to the right. We could even plug this in if we wanted, 3.75. Okay. This is how you set up all of your explosion problems. The trickiest part about conservation of momentum is just identifying what equation should you use, right? You have your three. Really, it's just one equation. It's always this one. Just do you need to combine the masses before or after the collision? And if you don't need to combine them ever, that's just your base equation.